Good afternoon, everyone. And I am Dr. Gaurav Ajpei. I'm working as Assistant Professor, Department of Mechanical and Automobile Engineering in BBU Lucknow. So, are you audible my voice or not?
Yeah, it is audible.
Audible. Okay. My slides is also visible to all or
Yeah, visible.
visible to all. Okay. Thank you, sir. Thank you very much. So, in this talk, I want to give a present deployment of metal matrix composite by powder metallurgy using cold isostatic compaction chamber. A review. Nowadays, the powder metallurgy is one of the, in this talk, I will cover the introduction, process of powder metallurgy, flowchart of powder compaction, design of isostatic compaction chamber, some mechanical properties, and some application of isostatic compaction chamber. So, as we discussed, I listen lot of talks in this ICMRTD conference. The nanoparticles, you can also make the nanoparticles from the powder metallurgy. Powder metallurgy is a highly developed method of manufacturing reliable ferrous or non-ferrous parts made by mixing elemental or alloy powders and compacting the mixture in a die. The resultant shapes are then sintered or heated in a controlled atmosphere furnace to bond the particles metallurgical. So this is a whole phenomena how the powder metallurgy works. Basically, it is a very one of the most advantage process because there's a no chip in forming the metal chipless metal working process. The powder metallurgy typically uses more than 97% of the starting raw material in the finished part. This is one of the most advantage from this powder metallurgy, and also it is a very energy and material converging process. So nowadays that's why people are adopting the powder metallurgy, and it gives also the very high density and strength.
So, what is the
So
minimum
I'm
dice?
just want to just discuss the powder metallurgy process. How can, yes sir, you can ask something. Yes sir.
What is the
Hello.
minimum dimension we can achieve by this powder metallurgy process?
Sir, we can make the samples like 10 and like some components of the automobile, like the component of the gears. So these types of components we can prepare using the powder metallurgy. So your dimension should be 1 to 50 This is a dimension allotted in the powder metallurgy section.
No,
So
I want to know the achievable dimension after powder metallurgy.
So you want to achieve the what? You want to achieve the some component waste powdered dimension. You want to achieve the some minimum dimension.
Yeah.
I'm not actually not consider your question. Not just listening. Not so. Please, can you tell me the which type of dimension you want actually?
The minimum
Hello.
size which we can achieve by this technique.
Minimum size, sir, if you want 1 less than 1 because in powder metallurgy we can prepare the nano composite, and nano composite then 10 ki power minus 9 nanometers, so you can achieve the nanoparticles also here.
And
Hello.
how much you have achieved?
Sir, actually, I prepared some nano composite material. So I achieved 1 less than 1 and also prepared some samples. So like 10 So I am just really because I worked last 10 to 15 years in this area. So I give the dimension like 10 to 15 you can easily achieve. But if you have a desire to go the lesser dimension, then you can also achieve. But you should have a good knowledge of density and porosity. So that is one of the major challenges in this area nowadays.
Okay, please proceed.
Okay, sir. So this is a powder. In this slides, you can see the powder metallurgy process. So first of all, you're taking the powder, and then after that you mix in the using the ball mill, planetary mill, and then ball planetary mill. Then you can go for the compacting. Then compacting, you can use the this device, and after that you can prepare the you go for the sintering, and then sintering you can achieve the some this type of elements. So now the more focus is only the compacting, because compacting is one of the more crucial role in the powder metallurgy. That's why in this talk, I will taking the cold isostatic compaction chamber. So first of all, I just want to here represent the powder compaction. So you can see the slides. There's a two type of compaction: uniaxial compaction and isostatic compaction. In the uniaxial compaction, there's a three methods: single piece dies, split dies, and double. So are there any questions, sir? Hello. Single piece die, split dies, and double piece die. And the isostatic compaction, you can use the hot isostatic and the cold isostatic compaction. So in the single piece die, the split die, and double piece die, there is a lot of problems regarding the porosity, regarding the density. But if you use the cold isostatic, means you can apply the same pressure in all the direction. You can achieve the lot of good components for the application purposes. So the isostatic compaction, I want to here just again, in this type of powder compaction, hydraulic arrangement is used to compress the powder. It operates according to the Pascal law, implying that the pressure at a static fluid point is the same in all the directions, like this. So the process of isostatic powder compaction, I want to here once again repeat. First of all, you fill the container with a metal powder, then heat under the vacuum to remove the volatile containments, then hermetically sealed container, and then apply the pressure and heat. And after that, you can achieve the very good and very non-porous sample. So this is a process of isostatic powder compaction. So this is again, I want to, because in the drawing the design of cold isostatic compaction chamber, this paper I have published already. This is the three types of pieces in the cold isostatic compaction chamber: ejector, die, and punch. And these samples I have prepared in the Abacus software, and then according to a literature survey, we can use the 600 megapascal, the yield strength of the sample. I'm using the EN 10269, and using the factor of safety, then I prepared the strength, I prepared the allowable strength, and then I find out the outer diameter of the sample. That is the 196 mm. This is a drawing of cold isostatic compaction chamber, which I have drawn in the AutoCAD software. And this is the image of the compaction chamber. You can see this image. This thing I prepared in the IIT laboratory in IIT Kanpur also. And after that, I am using this process of cold isostatic chamber in this UTM machine, and prepare the very fine and very good sample, whatever asked by the session chair, which type of dimension you can achieve. So we achieve the small green pellets from this very defined green pellets from the sample in this isostatic compaction chamber. Then after that, I prepare the aluminum nano alumina. And then if you see the FESEM image, you can also, there's a uniform dispersion of the nanoparticles into aluminum matrix. And also the 2%, I have achieved a very good strength, like compressive strength, indirect tensile strength, and Rockwell hardness. We can achieve up to the 2%. So this is the application part: industrial ceramic pressure forming, and high temperature refractory hard metals we can achieve from this cold isostatic compaction chamber: crystals, real metals, powder molding, and magnetic material. These are my references. Thank you.
Good afternoon, everyone. Very first, I'm fortunate to here to present my, you can say there's some findings, interesting findings in this new era of the 3D printing. I know 4D printings are there, but still I'm in healthcare sector, and still it is a new for our healthcare sector, and there are still challenges and innovative ideas that I would like to deliver here. So begin to my presentations here. I would like to present some, you can say 3D printing, what are the different definitions as per the regulatory agencies, what are the advantages, and here I'm so some methodology like apart from healthcare applications, the methods of 3D printing in general, very brief way, because there are so many methods, but here in considering the healthcare applications, what are the methods are at present available, limitations of 3D printing techniques that I will show you, and challenges along with this, my conclusion. Now begin with the introductions. It is the convergence of 3D printing technology and personalized medicines has captured significant attentions within the pharmaceutical sector. As we have so many diseases, like all the diseases, it may be not fixed like that. One treatment should be ideal for that. Okay, so that's why the personalized, tailor-made medicines are now gain a very important advantage here. And the 3D printing technology is one of the benefits that give the personalized to. The process of 3D printing is defined by the FDA, that is Food Drug Administration's US FDA, that is the creations of three-dimensional objects through the incremental buildup of materials. It is, you can say that we are adding layer to layer, and then what object we want to design exactly we form it. As per the according to the GOA, that is the United States Government Accountability Office, 3D printing is groundbreaking manufacturing technique. Means again, the entire theory is here, that is a layer by layer. And this directly from digital model means this is a use of the some digital, you can say software based technology CAD, and then you can have a desired shape, and then you can result into the fabrications. So this is the applications that we have seen in the healthcare, that is generally medical equipment. That is the first previous application, means the first application was found in this medical equipment, then slowly in this prosthetics and implant, then tissue and biomaterials and anatomical model. But now what exactly I am here, that is to present the personalized drug, or you can say therapeutic delivery. So there are so many innovative drug delivery. Even one of the product is recently approved by the US FDA. Then oral cavity, transdermal, pulmonary insert and implant. So other than you can say tissue and biomedical engineering, there are the very popular applications of this 3D printing in drug delivery too. So here 3D printing medicines, 3D printing tissues, personalized drug, customized prosthetics, and the medical device. With use of these all here, that I have made some statistics on, you can say. So I have referred papers, clinical papers, view papers, and statistical data, compiled research papers, reviews with the very keywords, right? That is ocular, skin, vagina, rectal, ear, oral tissue, dental. These all are, you can say, the keywords for what I have made, and these are the different search engines I have used. Why I made the such kind of the search methodology to increase the review rationality, or you can say after literature compilations, one can able to see that there is a any duplications, or you can say any applications is already found, so that protect, or that may you can say resist you to do the IP, further intellectual property protections. So this is my first step. See, this is the number of instances I have found for this. As I compare the other drug delivery system, means apart from 3D printing, I am definitely sure that this is a very less number of applications I have found, and this mostly in the tissue engineering, that is in prosthetics and other. But I'm definitely sure that in drug delivery applications there is very less, but there is a wide scope even, right? Okay, so here at the end I will summarize also what are the at present challenges and the limitations. Now these are the patenting trends we have at our university, PATSEER. And this PATSEER is our license version, and by again this, you can say, the many key strings I have applied, and you can say by booleans and everything I have made there. And this is, I found that it is very less number of patents that are applied in the pharmaceutical sector. This is only the figure that you can see, that is of pharmaceutical sectors only. So there is very you can say limited applications. Sorry, there is a scope of applications, but very limited filing here, you can see. Now next, I'm just focused the 3D printing methods. There are many 3D printing methods available. Rightly, I'm doing with extrusion, but there are liquid solidifications and the powder solidification techniques are there. So here in this diagram, we can see that there are the total 6 techniques. There's 2 techniques for liquid, 2 for powder, and 2 for extrusion. In extrusions, the fuse deposition modeling is widely used. Right. Okay. So if you can see, the other than healthcare application, there are so many choices available for filaments. Right. We can easily take the filaments and we can make the desired shape and size. But when it comes to the healthcare applications, there is one of the most challenges we have get, that is of biocompatibility, or you can say that is the degradations profile of that particular filaments. Even drug. We can't have in the drug, you can say, itself into the filaments, right? Okay, so there is a little bit challenge for us, that we require to have some specific extruders where we can even fabricate the filaments first, right? And that filaments, you can say, it is a composite of drug and along with the polymer. and then we can process into this further into the desired shape. So that we can consider as one of the challenges, right? So out of this circle, I'm using the fuse, even I'm enough expert to handle the fuse deposition modeling. Even I can build the some shape desire, and even after clinicians meeting, we can come with some 2-3 application also that I will later share you. Now, this is in general process of from how we can have the computer aided designs model to the finished product. So this is the, you can say, first we have the some CAD designing, and then we have the slicer software, and then we have the machine setup. Then finally we can do the printing process, and what object we can get, that you can say it is a 3D print agent. This is just in summary. Now, what are the limitations? Yes, so there are so many applications of 3D printing, but yes, exactly here I would like to pose some limitations in pharmaceutical field. Right now, what are the limitations? So very first, it is the environmental impact. Why? Because we are using the some sort of you can say plastics, polymers, right? Okay, so mainly that degradability, or you can say compatibility, may not be good for environmental friendly, right? So always we require to think of before you can say utilizing the 3D printing, we need to decide whether to bear this environmental cost or to explore the alternative solution. But when pharmaceutical applications as concerned, say example, the cancers, the implant for the cancer, there is a slow delivery of the drug at the you can say particular, you can say the oral cancer, or at the type of cervical cancer or the breast cancer, then definitely then we can compare the environmental, but yes, we can go for the alternative solutions, right? Okay, so very first, that in pharma, one thing is restricted to us, that is just so much, like you can say the availability of biocompatible materials. That is very, you can say, when I searched the when I started the work with my PhD scholars, right? Okay, we feel little bit difficult in finding the biocompatible and biodegradable filament. That is only the availability of the polyvinyl alcohol filaments at the market, that it only claim that is a medical grade. There are PCL and others, but they are not fully medical grade. Okay, so that is the one the things that limit us in the pharmaceutical. Then variability in the quality of 3D printed object. Yes, flexibility. Say example, next I will show you that I am targeted one 3D printing object that is for, you can say, vagina to intrauterine devices for uterine fibroids, right? So when I met the clinicians, they say, yeah, flexibility is very important, because property and other, you can say, IUDs available, intrauterine devices available in the market. That is, you can say, for diagnosis rather than the treatment. But fine. So here, if I'm having the availability of the filaments that is a biomedical grade, but I can't reach to the flexible structure of that, right? So this is again the new dimension or new limitations to make this as 3D printing in pharmaceutical. Okay, then safety and efficacy of 3D printers. Yes, because we always require to have some sterile, or you can say some this thing. Okay, so there may be a risk of some defective 3D printers and printing failures, which may compromise, you can say, little change in the object shape and you can say dimensions, or that, then it may be compromise the final efficacy of the product also, right? Then pharmaceutical policies. Yes, I see, since I'm working with the regulatory aspects on the various pharmaceutical products, I have not seen any of the particular, you can say, regulation or guideline or protocol that particularly pertaining or tell us that it is, you can say, that implementation of the effective 3D printing technology in the pharmaceutical field. So this is, I consider it is a greater limitations of 3D printing in pharmaceutical field. Now, what are the challenges? These challenges I have outlined based on my experiences to work with this. So the first, there are three types of challenges I have worked with. That is the technical challenges, regulatory challenges, and good manufacturing practices, means at the manufacturing challenges. Now, what are the technical challenges? As I have earlier told you, that it is inadequate mechanical properties, right? Okay, because we are not available the great materials, or you can say the series of biocompatible, biodegradable filaments, right? So that we require to always to compare the mechanical properties. It is difficulties for further processing and packaging also, accumulations of unprinted materials, then robust process control strategies required, right? And low production rate, so it is very time consuming, because there are advanced 3D printers are available, but I have not seen for particular which claim it is for pharmaceutical and further you can say healthcare devices production. So these are the technical challenges. Regulatory challenges, I already told you that, okay, there is a no well implemented guideline and standards even given by the US FDA regulatories, or you can say EMA, that is European Medicine Agency, and other type of this. So there is a lacking of the specific guidance from the regulatory authorities. Then issues of liability and responsibility, that is need to be addressed for this thing, because where it is utilizing community and hospital pharmacy, means each and every persons need to be trained, and accordingly they need to be worked. Then GMP challenges, yes, of course, that is the ease of establishing the GMP requirement. So I can't consider it is a challenge, right? But yes, whenever we can have any specific equipments for pharma application, that it must be a 21 CFR Part 11, right? So I don't think that 3D printer equipment calibrations and validations as specific qualification as per the 21 CFR Part 11. So these are the some challenges I pose from this. Now here I would like to tell you some glimpse of my research, which already completed by the PhD scholars. We have targeted the uterine fibers, where we have working on off-label use of the raloxifene and mifepristone. We work with the two approaches, that is simple drug-eluting insert, that is by melting, and one is a 3D printed object, that is we name is intrauterine, that is the devices. Now we completed even pharmacodynamic experiment in rabbit also, and we surprisingly found that this is 3D printing object is you can say highly promising in treatment of this you can say uterine fibroids as compared to marketed our this you can say reduce the complete fibroids of the same size and dimensions within 30 days, right? So it having the great potentials, and this work all carried out with the guidance of Dr. Jignesh Patel, gynecologist at the Surat. And because of his involvement, we actually bring this kind of things into the commercial also, because actually we consider this work, considering that in vivo property or in vivo aspects of these particular patients also. Now, these are the some research outcome. We have complete specifications file on that. There are some publications already accepted for this. Now, this is the second research that I would like to tell you. That is a 3D printed vagina insert. This is not for uterine target, but this is for vagina insert. That is my FDM technology. So far, we have completed the in vivo work also, and we got the very good and promising results, right? Okay, as we see that any vaginal continuous that tablet is available, I think ketoconazole and this, but it having you can say limited you can say the residence to the particular vagina. So that is always a chance of that recurrent, right? Okay, so this particular type of devices that gives us very, very slow release, and it degrade in you can say in situ only, right? Okay, so these are the advantages we always get it. So this is two research I have already completed, and I am more focusing on next is ocular, and there's a transdermal. But as I pose the greatest limitation, only the choice of materials. So at the end, I am conclude my talk here with the application of 3D printing in medicine represent one of the most disruptive technology with the genuine potential to transform the field of healthcare, right? Means we can have options to make it personalizing. Even that disease like the cancers, we can also, you can say, design the very good implant and insert based on the 3D printing technology, right? So it is transformative power lies in the ability to make the healthcare more affordable, accessible, and tailored to individual needs. However, this is the one of the restricted to me that the safe regulation of 3D printing with biomaterials is need to be established, right? So this is the bottom line of my presentations. I hope I can make my talk interesting in that. Yes,
Harishankar Bishwas from the Department of Chemistry, Surendranath College. I am presenting here advanced characterization techniques in nanocarbon materials and solution review. This is the my review paper also. And I work on the hydrogenated diamond-like carbon thin film, and also graphene oxide and graphene. Okay, I have used this type of instrument to characterize the material and in various applications. So fundamental working principle of some characterization techniques is shown here. I used for the analysis of the graphene or graphene oxide based nanocomposite that come under the scope of the present thesis also. My thesis also on that topic. And these protocols of the various reaction and studies undertaken have been also described by this picture also. And I use or I synthesize the hydrogenated diamond-like carbon. This is a new material though, because you know graphene and graphite and graphene oxide, various type of material, new material, they own the Nobel Prize also. But diamond-like carbon, that's mean it is actually the intermediate of graphene and graphene oxide, because it is hydrogenated graphene also. It is also known as graphene. Okay, so I synthesized this type of material and I characterized, and it is very near to diamond also. So I am not going to details about my work, but I am going to about my characterization techniques. And that was the lab where I am working. There is a AFM. This is a atomic force microscope, micro Raman vacuum, FTR, goniometer. This is the plasma machine that's by which we can synthesize this type of material also. And TEM is there in the other lab. And what is atomic force microscope? And this is a very sophisticated instrument. So how does the atomic force microscope, that is AFM? AFM provides a 3D profile of the surface on a nanoscale or in the nano thin film by measuring the force between a sharp probe and the surface at very short distance. It is about 0.2 to 10 nanometer also. The probe is supported to the flexible cantilever, and the AFM tip gently touches the surface and records the small force between the probe and the surface atom. Okay, and it may in the various way, that's mean it may touches the surface, or it may non-contact process also is there. And there is contact process and non-contact process. So if it touches the surface, then it is contact process. It does not touch the surface, but it can measure the force between the surface and probe. Then it is known as non-contact process. So how are force measured? The probe is placed on the end of the cantilever. There is another cantilever which is attached with the machine, which one can think as a spring like this. The amount of the force between the probe and the stem dependent on the spring constant, that is stiffness of the cantilever and the distance between the probe and the sample surface. This force can describe using Hooke's law also. And we know the Hooke's law of force proportional to x. And where F is the force, and if we need the force constant, then we F equal to minus K into X. So if the spring constant of the cantilever, it is about 0.01 to 0.1 Newton per meter, is less than the surface bends at the deflection is monitored. This typically result in the forces ranging from the nanonewton to micronewton also, in opinion. And how it can act? This is there is a piezoelectric in which a cantilever is bound to it, and this piezoelectric is moving, and then the cantilever also deflected like this. This is the surface, and this is the cantilever, and a laser light just tipped on the tip of the cantilever. Then it moves, and we can move the surface also, or we can move the tip also. So this is a scanning process. So scanning in the contact process, tip follows the profile of the surface like this. This is yes. So like this is the cantilever is moving on the surface, and then it forms, it measures the force, and by the force we can draw the three-dimensional graph, which is the image. Actually, we know microscope means we can measure the micrometer up to micrometer. Okay, but we can or we can see the up to micrometer. But atomic force microscope is, it can measure the nanometer. Okay, up to nanometer surface. So how it can work? Actually, it is indirect image. It is not direct image. We can not see the direct image. So most of the electron microscope and the atomic force microscope, it can form the indirect image. That's mean we can measure the force, and then we can this force can be converted to a three-dimensional surface image. So by this way, we can get the actual image of the surface. So piezoelectric translator in this way, atomic force microscope working. And this is our actually our sample that's been hydrogenated diamond like carbon. We have measured up to 60 nanometer area. Okay, and this is the three-dimensional image of the hydrogenated diamond like carbon surface. This is this material is also very nano. That's been the thickness of our material is 180 nanometer only. Okay, so we can't see it by naked eye, but since we synthesize on the silicon surface, then we can clearly see by naked eye. And another instrument is we have used a transmission electron microscope. That's been this is the schematic drawing of the TEM image. So not TEM image, the TEM instrument. And this is the ultra-structural study, electron microscopy, and resolution based at about 0.2 nanometer to 10 to the power minus 9 meter. It is 1 nanometer, and which is about 1,000 times better than ordinary light microscope. So TEM is the far more useful for medical investigation than SEM also. We will discuss about the SEM. The electron source is typically a heated tungsten filament or a field emission gun. So field emission guns are preferred due to their high brightness, providing a more coherent and focused electron beam. So this is the overall instrumental scenario. And major use of the TEM, we already said that renal diseases, typical tumors, muscle diseases, skin diseases, miscellaneous diseases. For this use, we can mostly use this TEM image. And SEM, what is the SEM? Scanning electron microscope. So electron gun, we use an electron gun then in the instrument, and then it gun the electron to the surface. You can see that it is like a sample surface, and then so many electrons just eject from the electron gun and penetrate on the surface. Then some electron just carrying that's been reflected, and detector can detect this type of electron, and in this way we can get image. Okay, computerized image. And the fundamental principle of SEM involves a scanning of focused beam of electrons. We already discussed about it, and this is the overall scenario of the instrument. In this in the instrument, this type of working is doing, and there are so many segment of the instrument: vacuum chamber, electron gun. There is an anode, electron optics, magnetic lenses, and backscattering electron detector, and then the secondary electron detector. And from here, this is amplifier, and we can get the image in the computer. And same and TEM, there are some differences also there. One is tunneling electron microscope. That's an electron is
Dr.
tunnel.
Harikema, sir, can you conclude?
Yes, yes, sir. Yes.
I'm going to present my presentation on the title of the morphological and optical study of the thermodynamically synthesis nickel oxide nickel sulfide nanocomposite. My paper ID is the 247. The content, the introductions, synthesis, characterizations, and conclusion. Let's see the introductions. Now, the nanocomposites offer the inherent mechanical properties, improved thermal and electrical properties.
Just discuss on synthesis, method of synthesis, optical properties, and conclusion.
Okay. So first we use the thermodynamical method. So first we take the 0.2 molarity of the NOH in 25 ml distilled water and stir in the 15 minutes. And then we second the 0.2 ml molarity of nickel nitrate in 40 ml distilled water, stir in the 30 minutes. And we add the NOH in nickel nitrate. Then we stir in 3 hours, and then we transfer to autoclave and we heating the furnace. Now we centrifuge the solution, then we dry in the oven and we get the green powder, and we get the centrifuge calcination at 35 degrees Celsius for 1 hour, and we get the nickel oxide. First we take the 0.1 m molarity nickel oxide in 50 ml distilled water, stirring at 30 minutes. Then we take the 0.1 m molarity of sodium sulfide in 50 ml distilled water and stir in the 15 minutes. After the 15 minutes, we add the sodium sulfate in nickel oxygen, and we transfer the autoclave and heating the furnace, and we centrifuge and we dry in the oven, and we grinding, and we get the nickel oxide, nickel sulfide nanocomposite. Now with the characterizations, the first characterization is the XRD. This is the XRD pattern, and we are perfectly matched with all the nickel oxide, nickel sulfate, JCPDS. This nickel oxide, nickel sulfate nanocomposites were found to have hexagonal crystal structure.
Okay.
And we calculate the lattice parameter with the hexagonal crystal structure, and this is the table. Now this is the Levi-Sharrer equations and Williamson-Horst plot. This is the slope, and this is size strain plot equations, and this is the slope, and we get this is a table of all the calculation of crystallized size and strain. Now the visible spectroscopy reveal about the optical properties. The observation of the sample was seen the both ultraviolet and visible, rezoning range for 2 nm to 50 nm.
So
Now
in
the
which
top-
solvent you disperse your powder, or you show DRS method you use?
DRS.
Okay.
Yeah. This is a top plot method, and we get the 1.3 band gap and refractive index equation. This is a different. This side, the right hand side, the band gap one, and the refractive index was found to be 3.12. Now the FESAM. The FESAM 2D nanosheet morphology forwarded by the communication of the nickel oxide and nickel sulfide, offering a highly structured morphology with the nickel oxide nanoparticle display on the nickel sulfate film. And this is the EDX. It shows the preference of nickel, sulfur, and oxygen. Now the conclusion. First, the nickel oxide, nickel sulfide nanoparticle where synthesist used the hydrothermal method. The nanostructure material was characterization by SAM, XRD measurement, morphology analysis revealed two-dimensional nanosheet, which are the thin, flat nanoparticles with structure comparable to sheet or file. And the last, the nickel oxide, nickel sulfate nanoparticles show an expectational decrease in the band gap 0.13 eV, make them suitable for using the solar cell applications.
Okay, thank you.
Thank you.
Thank you.
Any question?
No, thank
So, good morning to all of you, and thanks to the organizers for providing me this opportunity to present my work here. The main motto behind this work is to introduce magnetic compton scattering to the audience, and as an application part, I have used lanthanum magnites. So, in this discussion, we discuss the magnetic characteristic of lanthanum magnites using magnetic compton scattering technique. So first of all, give the brief introduction about the Compton scattering. What is Compton scattering? We all know that Compton scattering occurs when a photon interacts with an electron and is scattered with a loss of energy. That is an elastic scattering. And this electron have a wave function which is produced the electronic properties of that material. Using this wave function, we can calculate magnetic Compton profile, and this is the further process we will discuss here. That This scattered photon have change wavelength, and this change in wavelength is given by this equation, that is delta lambda, and this has final or initial difference between final and initial wavelength. But in this process, we have two most important assumptions, that is electron is free and electron is at rest. The first assumption is occur when your initial wavelength is less than the final wavelength, and the second assumption is to simplify that in electron distribution in momentum space.
Yeah, sorry to interrupt you, Dr. Singh.
Yeah.
Yeah, slides change is not visible. Slide is only initial slide only we are seeing now.
Okay, changing is not seen by you.
Yeah, not seen. Only initial slide only we are seeing.
Maybe there is something problem. And this now.
Yeah, now it's okay. Now it's okay. Now it's fine.
Okay, it means in full screen mode there is some issue.
Okay. You can continue like this.
Continue like this.
Yeah, you can continue like that.
Okay, thank you. So these two assumptions are in the normal component scattering, but in real materials, what happen? Electron is neither free nor at rest. So there is some difference between the change in wavelength that is occurred in this equation, and this equation is slightly different from this first equation, because the h upon m naught c 1 minus cos theta is similar to this the first term of this recoil term, but the second term occurs due to the broadening, and that broadening is known as Doppler broadening, and this broadening gives the information about the Compton scattering. So the electron associated this broadening give us the information about magnetic Compton profile, and therefore we can say that the magnetic Compton profile or magnetic Compton scattering have information about the electromagnetic wave function as well as magnetic moment of that electron. So using this broadening, using this wave function, we can calculate the magnetic Compton profile by the following these equations. Let us that if we have a wave function psi r of the in position space, then using this wave function in position space, we can calculate momentum space wave function that is given by this equation, and using this momentum space wave function, we can calculate electron momentum density of that system or that electrons. So this is the formula for calculating the electron momentum density, and using this electron momentum density, we can calculate the Compton profile using the double integration of this electron momentum density. Now, if we calculate area under the curve of this Compton profile, then it gives the total number of electrons of that system. It means this Compton profile give us the total information of the charge within the system. This is the this process is known as the charge Compton profile of that system. But we know that the electrons are present in spin up and spin down, or we can say that majority and minority electrons. So if we measure the charge Compton profile for separately for spin up or spin down electron, or we can say that majority Compton profile and minority Compton profile, and subtract both these Compton profiles, then we can calculate the magnetic Compton profile by subtracting majority spin electrons, minority spin electrons from the majority spin electrons, and this separation given by this equation. And if we calculate the area under the curve of this magnetic Compton profile, then it gives us the total number of unpaired electrons. It means the total spin magnetic moment of that electrons. If we calculate this magnetic moment using the experimental data, then this formula is used. So what is the difference between the basic question is what is the difference between different magnetic moment calculating techniques and magnetic Compton scattering technique? So using such like a skewed VSM etc. technique, we calculate total magnetic moment of that system, not spin magnetic moment of any system. So the motive behind the magnetic Compton scattering is to determine spin dependent momentum density of magnetic electrons as well as elemental specific magnetic moment of that system. So we have used spring at the spectrometer available at BL0 at W Spring at Japan that have 10 solid state germanium detectors and synchrotron radiation with high energy. That energy and the secondary parameters we will discuss in further slide. But if you want to know more about this spectrometer and this process, then the reference is given here. This is the photographic view, and these are the basic parameters we set when we take the measurements. So the energy of that synchrotron radiation is, we can set here 182.8 kilo electron volt. That is very much high, and the sample size is very much small, that 2 mm, 2 mm and 6 mm. And the beam size incident on that sample is 0.8 mm, 0.8 mm and 0.8 mm. The scattering angle is 178. It means the scattering is nearly back scattering, and the applied magnetic field change with within 1 second. That means parallel and anti-parallel orientation of the magnetic field applied on the sample. So we can measure the majority and minority spin electronic behavior with the system. After taking the data, we have applied some data corrections to take the magnetic component profile data. That these data corrections are like beam instability correction, detector efficiency correction, absorption within the sample, magnetic cross section, etc. Now, as we get the magnetic component profile data for majority and minority spin, then the both data for majority and minority electrons shows same pattern, which is shown in the this graph A. But when we compare this data, then we find that there is a slight difference between the Compton, at the Compton peak in both the spin up and spin down data, or we can say majority and minority spin electrons. If we take the difference between both these, then we find that magnetic Compton profile, which is shown in the graph C. It means this peak, or we can say that the channel number in between 1000 to 150 have nearly shows the spin electrons, and the further in both side, left and right side, shows the core electron behavior in the Compton profile. So when we change these channel numbers in momentum space, then we find the Compton profile data. So now this is the application part of lanthanum magnetite, which is doped with nickel and cobalt transition metals. So the data taken at different temperature using the magnetic Compton spectrometer and converted into the momentum space, then we find that in higher momentum space, that magnetic moment should be 0. It means in higher momentum side, there are core electron contribution presents. So as the base LCMO, which is not doped with nickel and cobalt, have that Curie temperature lower than room temperature, it means we find the maximum moment at the lower temperature, which is also shown in these graphs, that shows that maximum magnetic moment found at Kelvin temperature for this both these sample using magnetic Compton scattering technique. So this graph shows the spin magnetic moment only. But if you want to calculate the contribution of different elements within this sample, then we decomposed our magnetic Compton profile data into its different components data. So we found that in both these samples, that major contribution have due to the Mn 3d electrons, which have parallel or ferromagnetic behavior with the nickel and cobalt electrons, while the diffuse electron have anti-parallel behavior with Mn 3d electrons as well as nickel and cobalt 3 electrons. To find the orbital behavior in this sample, that how orbital magnetic moment behave in this sample, we compare our data with the MCP data, VSM data. It means VSM provides us that the total magnetic moment in the system, while the MCP have give us only spin magnetic behavior. If we compare both the data, then we can calculate orbital magnetic behavior within this system. So this graph shows that the orbital magnetic behavior is negative trend. It means that the spin magnetic moment is higher than the total magnetic moments. So the difference give us the orbital contribution. Here we can see that in both the sample, cobalt and nickel doped, Mn and the doped transition metal have parallel or ferromagnetic behavior with each other, while the diffuse contribution have anti-parallel contribution with each other. It means that diffuse electrons have negative magnetic moment within this system. This is the table which give us the total magnetic moment, spin magnetic moment, and decomposed magnetic moment within the system. If we compare our diffuse magnetic moment with orbital contribution, then it is found that the orbital magnetic moment occurs due to the diffuse electron contributions. So thank you. If you have any question.